Hello guys, here I'm going to present the extension of magnetic moments, that is the paramagnetic and diamagnetic susceptibility, and its property known as hysteresis. First, here is a glance of what actually is a paramagnetic or a diamagnetic substance. So when you have a two magnetic poles like north and south, for a diamagnetic substance, the magnetic lines of force, they are, you can see that they are being repelled here in this direction and in this direction. And there are a lot of gaps there. But for a paramagnetic substance, the magnetic lines of force tend to pass through this. Here you can see this region, there is convergence. Here there is divergence, and here there is convergence. So this is the direction of the magnetic field strength H, which we have already seen in the last class. So here is a brief description. So you can remember that magnetic lines of force pass through paramagnetic, pass through para. This is a kind of keyword that you can remember to draw when you want to describe this. Okay, again, the in the next part, we can see about the ferromagnetism and paramagnetism. But what I am going to concentrate here is the graphs there. Okay, and there is the magnetic susceptibility here. This is chi. Okay, this is the magnetic susceptibility. That is how far it can catch up the magnetic moment. That is represented by this word key. And here you have this temperature. Okay, right now you can see that for paramagnetic substance, as you increase the temperature in this particular direction, as you increase, there is a decrease in the paramagnetic substance, paramagnetic property. So this is going down. Gradually this is going down when you increase the temperature. So for paramagnetic substance, temperature reduces the chi. Chi you can consider as some magnetic property or magnetic induction, and that you can see here in terms of the domains here. You can see this, the domains there. So here you have got each individual lone pair of electron. I mean, it is individual electron in particular direction responsible for the paramagnetic substance. And you can compare this with the ferromagnetic substances there. In the ferromagnetic substance, you have got everything aligned, and this the psi is having thousands of such domains which give integrate to give a magnetic field. But look at the antiferromagnetic, some antiparallel moments are cancelling it. Here this and this gets cancelled, everything is getting cancelled. And in the ferromagnetic substance, you can see that this one is larger and this one is smaller. That is, the magnitude is not balanced. Magnitude is not balanced. So here we are going to see the graphs again pertaining to ferromagnetic substance and paramagnetic substance is given there. So here is chi, the value of chi is there. Then you have the temperature. So as the temperature increases, you can see that the ferromagnetic substance also loses the magnetism. Okay, so this is a very steep decrease. Okay, steep decrease in magnetic property. This one. Okay, so after certain temperature, which we note here as Tc, the substance behaves just like a paramagnetic substance. Okay, now that is what you call it as the Curie temperature. The Curie temperature is the temperature at which the ferromagnetic substance, right, the ferromagnetic substance behave like a paramagnetic substance. After this particular point, here is this particular point Tc. So the ferromagnetic substance starts to behave like a paramagnetic substance. Okay. Now you can take the case of antiferromagnetic substance. When you increase the temperature in this particular direction, there is an increase in the magnetic susceptibility in this direction. You can see this magnetic susceptibility high or magnetic property increases. So after a particular point here like this, this particular point is characteristic of the material that you are using. And this particular point is called as the Neel temperature when you have the antiferromagnetic substance going the paramagnetic way. Okay, here it is. This is the paramagnetic substance, paramagnetic behavior. And this is the two important graphs called as the Curie temperature Tc and Neel temperature Tn. Okay, for the ferromagnetic substance, the magnetic susceptibility decreases steeply and then it behaves like a paramagnetic substance. Okay, that is called as a Tc. And then for an antiferromagnetic substance, it increases rapidly and then it behaves just the same way as this one. So this is a paramagnetic curve, this is antiferromagnetic, this is ferromagnetic. So here is a point where you have got Tc and Tn. These are two very important aspects of the magnetic property. And here you can see that the theory behind them is, for paramagnetism is these are randomized by thermal energy, and when you apply certain temperature, they get a different ordered arrangements. So this ordered arrangements constitutes for the magnetic property. In the ferromagnetic regions, there are certain regions. I think here this is called as the domain. There are certain domains, in which these domains, can increase or decrease it. So for ferromagnetic substance, it is only the domain, but for paramagnetic substance, it is only the individual electrons. So that is how we are able to explain the magnetic properties of the certain materials. And this is a very characteristic graph of increase in the magnetic field with the orientation and the domain of that. So just you can next go to the hysteresis curve. This is what I have the main point of explanation today, the hysteresis curve. Magnetic behavior of different ferromagnetic substances is demonstrated by hysteresis curve. This is a plot of magnetic flux density which is given as B against applied magnetic field H. Okay, so you have to write H versus B here. Okay, H versus B there. Okay, now we look at the graph. Forget about these numbers for time being. You start from this point called as 0, 0. This is the origin there. So as you increase the H, you start with B and H are 0. Okay, that is the thing that I am writing there. 0, 0. If I write means like it is B versus H. So if you have B versus H 0, 0, there is no magnetic field and there is no magnetic strength. Okay, so it doesn't have any field strength and it doesn't have any magnetic field. Then suddenly what happens is if you just increase the value of H there, H is the magnetic field strength, the magnetic flux or the magnetic susceptibility it is induced in that particular thing. So as you keep on increasing the H, the value increases. This is how you have to start for a hysteresis curve. The B versus curve goes to a particular value and a maximum point of A is reached. This is a kind of saturation for the hysteresis curve, and it depends on the type of the material. Now this is, you can go on increasing the H and not down the H, but for a certain value, like for example 1200 strength of magnetic field, you're going to stop there and then you just reverse it. What happens when you reverse when you reverse, it doesn't take up this particular path, it doesn't go this particular path. The magnetic flux, it takes up this particular path. That means it has to come to 0 comma 0, but it is not coming to 0 comma 0, it comes to about 0 comma 1.5. Here as you can see, just this is just 1.5. That is, you are applying a magnetic field strength. The electrons are getting a particular electron magnetic moment, and they just retain the magnetic field strength. Even though you reduce the magnetic field strength, they are retaining it. It's not going to 0. It doesn't trace this particular path. It doesn't trace this particular path. That means it is having certain value there. So that value is described by this particular graph. Okay. Now you just change the phase, and you go into the negative value. What happens is, when you just change the phase, the magnetic flux further decreases and it comes to 0. And that further going down, it goes to a particular point. It's sufficient. You can see there. Uh, all the spins are aligned in the sample, but when the applied field is reduced, the flux density does not flow initial curve, but because initial curve is this one. Because of the difficulty in reversing process where domains have grown through the crystal infections, they do not trace the path, and instead they follow this particular path. You can just give some meaning data as x and x, x. A sufficiently large magnetic field in the reverse direction must be applied. You can just change the pride before the magnetization process can be reversed. So as you can see that this graph, further reduction, reduction is in terms of the h. Further reduction, it goes in the particular negative direction and it stops there. After a point D is reached, an increase in the h it doesn't go in this particular direct direction. Direct increase is not there. So it takes up a particular definite path. Okay, and it touches the x-axis here at this particular point, and then it increases. And again, you're coming back to the same current. When you started at 0 comma 0, it is not 0 comma 0, it is some 0 point, 1.5 comma 0 or something like that. That is reached there. Okay, so that is why it's called as the property that is dependent. So that path is not traced. Okay, the field need not to be applied. So that means, even if you are removing the magnetic field strength, then the important point is, even if you are removing this particular H, the magnetism is retained. Remove H completely, magnetism is retained. So it doesn't go back. So again, you have to uh, actually, if coming back to this particular point, it should be it should come to the origin 0 comma 0, but that is not there. So that is why the hysteresis curve represents a particular uh, induction of magnetic induction. Okay, so just to see that in the next slide there, here it is. There are a lot of curves there. The typical curve, which is having a flat increase there, and then sudden increase there, and plateaus there. Here you're getting two plateaus there, and this is a perfect uh, hysteresis curve you're going to draw in the examination. So this is a perfect hysteresis curve, but it is having a low coercivity magnet, and this is high coercivity magnet. That means you can see that you start from this particular point, it goes on increasing, and even if you are reducing the magnetic field strength, the magnetic susceptibility continues to remain the same level. That means the magnetism is retained to a very higher level. So here this is going to a lower one, and this one, in a soft magnetic metal, there is no such thing. When you increase the temperature, there is no increase, and only after a particular point you get a magnetism, and it continues to retain there. So that particular thing is called as the soft magnetic material. So hysteresis loops, they represent coercivity. Coercivity means how much you can coerce, how much you can induce, how much you can install the magnetic field, and that is the magnetic field strength. That is what is represented there. Okay, so these are the curves for certain permanent magnets, and maximum. These are some of the applications that they're going to use in, uh, in that particular property. For example, There is a property called as 1 comma 0, which we often call as the binary, and that is what we call as the digits. This is the difference that makes between digital and analog things. And certain magnetic properties, can also have a very good magnetism, like 1, and something which is below can be taken as something 0. So again, a very good magnetic hysteresis curve processing material can be taken for binary systems, such as, for example, you can see this magnet for this samarium cobalt 5 is there. So they are able to retain the magnetic for a long amount of time, even if you remove the magnetic field. This property is being used, in certain hard disks also. And here is a graph of certain materials, like for example, samarium carbonate, some other alloys are there, Mk steel, and then here it is a very good example of lanthanum compounds retaining that particular property. Okay, so this is how hysteresis curve is going to be very useful. And here I am going to give you an assignment. So this is how do you measure the magnetic susceptibility? Measure magnetic susceptibility. This particular ability is method is called as the Guy method. Guy. Guy. So it uses a kind of Guy balance. It has got a formula there that I'm going to give you an assignment. So you can see that there are north and south poles there, and is connected to a certain circuit. But here is your magnetic material. This magnetic material is still placed. So you just find calibrate this without any sample and find out there, and apply a magnetic field, and then you can place you can see that how this magnetic material is going to decrease or increase the magnetic susceptibility there. So that is what is the graph there. So you just give an explanation of the uh, Goy method, take it as an assignment. Okay, so I'm just summing up. This is a very beautiful graph of those particular things. You can see that the temperature is increasing in this particular direction, and magnetic susceptibility is this direction. So you have got antiferromagnetic substance. Antiferromagnetic substance, as you increase the temperature, magnetism is increasing in this particular direction, and here you have got a temperature called as a Tn. So after that it behaves, even though you will be increasing the temperature in this particular direction, it behaves like a paramagnetic substance. So Neel temperature is one when the antiferromagnetic substance begins to behave like a paramagnetic substance, whereas an entire paramagnetic substance, it starts losing this magnetic property when you just increase the temperature in this particular direction. So this is the direction. So this direction is a reduced chi. Okay, and there you have got ferromagnetic substance because it has got large domain of large region of ferromagnetic materials or electrons. It doesn't immediately lose. If it lose that, it should have gone this way. It should have gone this particular way. So there is no decrease in the magnetic. There is a sharp decrease in magnetic susceptibility, and after a particular point, which is called as a TC, it starts to behave again like a paramagnetic behavior. Paramagnetic behavior. So this is a very important grasp for you to remember about the three different properties. Antiferromagnetic, Neel. Ferromagnetic, Curie. FC. So here this is the way you can remember. FC, AF, antiferro, Neel. AFN, FC. Okay. So ferromagnetic substance begin to behave like a paramagnetic substance is the Curie point there. And this is a general representation of the ferromagnetic versus paramagnetic substance, which we call it the TC. Okay, and just to begin to summarize the uh, hysteresis curve with some description there, I'm just going to import one diagram there, and here it is. This is a very good explanation about the hysteresis curve. Here it is. So this gives an alignment also. So you start with 0, 0 here at this particular point, where B is 0, and H is 0. This 0 value is H, and this M is 0. So this M we have just seen as chi, magnetic susceptibility. It just keeps on increasing. Material follows non-linear magnetization curve and magnetism from 0 field value, so it itself increases. So there is a maximum magnetization. You just reduce this H in this particular direction. It doesn't come back. It goes like this. And when driving magnetic field drops to 0, the ferromagnetic material retains a considerable degree of magnetization. This is useful as a magnetic memory device. So that means it's got a very good memory. It doesn't go out to this particular thing. And here is described by a particularly important diagram. You do not have to draw this. Further reduction in H, it reduces the magnetic susceptibility, but it doesn't still go to the 0, 0, and that driving magnetic field must be reversed and increased to large value to drive the magnetism to 0 again. That's what it's telling is, again it is reduces, and again you are increasing the magnetic field strength from negative to the positive. So this is completely plus and plus, this is minus and plus, this is minus and minus, this is minus and plus. That way it is B and H are being resolved. So the hysteresis slip shows the history dependent nature of magnetic ferromaterial once the material has been driven to saturation. This is the point of saturation. Okay, the magnetism field can then be dropped to 0 and then retain most of its magnetization. So it retains, this is the important point there. It is the magnetization. So you just have to take up the assignment of the Gouy method, and you got another method called the Faraday method of measuring magnetic susceptibility. Just write it down and send that to me, and just assign some marks there. Magnetic susceptibility. Okay, so remember, hysteresis loop is very useful for uh, useful magnetic property magnetic property for memory. Okay, so you can find this some description about the notes in the description. Thank you for joining me. We'll see you soon.